On the afternoon of December 9th, 1968, nearly 1,000 computer professionals gathered inside a conference hall in San Francisco. Most of them believed they understood what a computer was. A computer was a large, expensive machine hidden inside a laboratory or corporate data center. It accepted carefully prepared instructions, performed calculations, and returned its answers on paper. Ordinary people did not sit in front of computers all day. They did not point at words on a screen, open linked documents, edit information instantly, or speak face-to-face through a network. Those ideas belonged to science fiction. Then, a quiet engineer named Douglas Engelbart took his seat beneath a giant projection screen, placed one hand on a keyboard, and rested the other on a small pointing device. The device looked like a wooden block with a cable attached to it. As Engelbart moved it across the desk, a bright tracking mark moved across the screen behind him. He selected words, rearranged lists, opened linked information, changed the way documents appeared, and communicated with colleagues working miles away. Live video of another person appeared inside the computer display. Two users examined and changed the same information together. The audience was watching a computer behave not merely as a calculating machine, but as an interactive workspace, a communication system, and an extension of human thought. The demonstration lasted about 90 minutes. Decades later, it would become known as the mother of all demos, because so many elements of modern computing seemed to appear in one astonishing presentation. The computer mouse made its public debut that day, but the mouse was only the most visible part of a much larger dream. Engelbart had not spent years trying to build a convenient accessory. He had spent years asking how technology could improve humanity's ability to think, organize knowledge, communicate, and solve problems together. His wooden mouse was not the destination. It was a key that opened the door to an entirely different relationship between people and machines. To understand how radical that vision was, we must return to a world before personal computing. During the 1940s and 1950s, computers were rare, enormous, and expensive. Governments, universities, and large corporations used them, mainly for calculation and record processing. A programmer might submit punched cards and wait hours for a printed result, only to discover an error and begin again. Users did not normally interact continuously with a machine, and there was no familiar desktop, pointer, or expectation that information could be moved and linked in real time. Douglas Engelbart asked a different question. What if computers could make human beings more capable? What if a machine could help a person explore complicated ideas, connect related pieces of information, communicate with distant colleagues, and improve the way groups work together? Instead of replacing the human mind, the computer could augment it. That question became the organizing purpose of Engelbart's life. Douglas Carl Engelbart was born in Portland, Oregon in 1925 and studied electrical engineering before serving in the United States Navy as a radar technician. Radar showed him that electronic information could appear visually on a screen and help a person understand a changing situation. While serving in the Philippines, he encountered Vannevar Bush's essay As We May Think. Bush imagined a device called the Memex, through which a person could store documents and connect related ideas along associative trails. Engelbart began imagining a screen-based system in which people could navigate information as naturally as the mind moves between thoughts. After the war, Engelbart completed his degree and worked at the National Advisory Committee for Aeronautics. Although he had a secure career, he wanted a mission important enough to justify his life's work. He concluded that the world's increasingly complex problems demanded better ways for groups to understand information and coordinate action. Computers, he believed, could become part of a larger system for improving collective human capability. He was not proposing a faster calculator, but a new intellectual environment. Engelbart earned a doctorate in electrical engineering at the University of California, Berkeley, but institutions found his broad vision difficult to support. It crossed computing, psychology, information organization, and social systems, while depending on expensive, immature technology. In 1957, he joined the Stanford Research Institute in Menlo Park. His 1962 report, Augmenting Human Intellect, a conceptual framework, argued that people already extended their abilities through language, writing, symbols, tools, and organizations. Computers could become another layer in that system if they were designed around the creation and communication of knowledge. Engelbart used the word augmentation deliberately. He was not trying to automate people out of existence. He wanted to increase their ability to understand and act. His ideal user was a knowledge worker facing a complicated problem, surrounded by information that had to be examined from multiple perspectives. Such a person should be able to write and revise ideas quickly, connect one document to another, change the level of detail being displayed, communicate with collaborators, and preserve a record of decisions. The computer should respond immediately, allowing thought and action to form a continuous loop. This sounds familiar today because modern users routinely edit documents, search databases, follow links, join video meetings, and collaborate online. In 1962, it was a blueprint for a world that barely existed. With support from government research agencies, including the Advanced Research Projects Agency, Engelbart created the Augmentation Research Center at SRI. He assembled a team of engineers, programmers, and researchers who were willing to work on unusual problems. Together, they began building a complete interactive environment called the Owen-Line system, usually shortened to NLS. It was not a single invention. It was a combination of hardware, software, displays, input devices, communication methods, document structures, and working practices. The team used the system to help develop the system itself, an approach Engelbart called bootstrapping. Every improvement in their tools could help them design the next improvement more effectively. In theory, this created a rising cycle of capability. A better tool made the team better at building tools, which produced an even better tool, and so on. One of the first challenges was simple to describe but difficult to solve. If information appeared on a display, how should a person indicate a particular word, symbol, or location? Light pens allowed a user to point directly at a screen, but they required the arm to remain raised and could block part of the display. Joysticks, trackballs, and other devices were available or under investigation. Engelbart wanted something accurate, fast, and comfortable enough to use, while the other hand remained near the keyboard. He reportedly conceived the basic idea during a conference lecture in the early 1960s. The device would sit on a horizontal surface and translate physical movement into movement along two axes on a screen. Engineer William English, known as Bill English, built the first working prototype from Engelbart's sketches. The body was carved from wood. Beneath it were two metal wheels mounted at right angles. One wheel measured horizontal movement, and the other measured vertical movement. When the user pushed the box across the desk, the wheels turned and generated signals that told the computer how to move the tracking mark. The first prototype had room for only one button. A cable carried the signals back to the system. No one on the team clearly remembered who first used the name mouse. The wooden body and trailing cable resembled a small animal with a tail, and the nickname remained. Engelbart's formal patent, filed in 1967 and granted in 1970, called it an XY position indicator for a display system. The patent described a handheld housing with perpendicular position wheels that controlled a cursor on a cathode ray tube display. At the time, the title sounded more reasonable than mouse because there was no established product category to name. The device had been invented for an interactive system that most computer users had never seen. Engelbart's team compared the mouse with other pointing methods. Its deeper advantage appeared inside NLS. A user could move a pointer, choose an object, press a button, and receive an immediate visible response. The screen became an active space rather than a passive output surface. The mouse was only one part of Engelbart's unusual control system. Beside the conventional keyboard, users could operate a 5-key chord set. Much like a musician produces different notes by pressing combinations of keys, an experienced NLS user could enter commands through combinations of fingers. Engelbart believed that trained users could achieve extraordinary speed by coordinating the mouse, keyboard, and chord set. His goal was not to make the system immediately obvious to a beginner. He wanted to create a powerful instrument that a dedicated knowledge worker could master, just as a musician masters a piano or a pilot masters an aircraft cockpit. This philosophy later created both admiration and difficulty. NLS could perform remarkable operations, but it demanded training and commitment. Modern consumer software would often move in the opposite direction, hiding complexity behind simple icons and menus. Engelbart believed that some complexity was worth learning if it produced greater intellectual power. NLS developed capabilities far ahead of normal computing. Practice. Users could edit text directly, reorganize material, view documents at different hierarchical levels, assign addresses to individual statements, and follow links within or between files. Graphics could contain linked items, while search tools, annotations, and messages helped a team maintain a developing record of its work. NLS was also a collaborative system. Engelbart's group did not think of the computer as an isolated personal appliance. They imagined people connected through a network, sharing information and improving a common body of knowledge. In the mid-1960s, this was an extraordinary goal. Computer networking itself was still experimental. Most machines did not communicate easily with other machines, yet the Augmentation Research Center was building methods for distant users to work together on the same material. The group's daily practices became part of the research. They wrote reports in NLS, developed software in NLS, managed projects in NLS, and used the system to discuss how NLS should evolve. The line between building the tool and living inside the tool began to disappear. By 1968, Engelbart and his team had created something powerful, but few outsiders truly understood it. Written papers could describe the system, yet the description could not communicate the experience of watching information respond instantly to a person's hand. Engelbart needed to show the system working. The opportunity came at the Fall Joint Computer Conference in San Francisco. Rather than deliver a conventional lecture, he proposed a live multimedia demonstration. The plan was enormously risky. The main computer, an SDS 940, would remain at SRI in Menlo Park, roughly 30 miles from the conference hall. Engelbart would sit on stage in San Francisco and control the remote system through communication links. The computer display had to be transmitted to the auditorium and projected onto a large screen. Cameras had to show Engelbart his hands and remote. Colleagues. Video images and computer graphics had to be combined in real time. Audio had to connect people in separate locations. Bill English took a leading role in designing and coordinating the technical production. The team used custom electronics, microwave links, telephone connections, cameras, projectors, and specially arranged control equipment. It was closer to producing a live television broadcast than giving a normal academic presentation. If the connection failed, the screen might go dark. If the computer crashed, the demonstration could stop. If the video switching failed, the audience would not understand what Engelbart was doing. There was no edited recording to hide a mistake, and no modern presentation laptop waiting as a backup. The entire argument depended on a live experimental system miles away. The team rehearsed carefully, checking signals, cameras, prepared documents, and Engelbart's communication with the production crew. On stage were a keyboard, chord key set, and a later 3-button mouse. The presentation was formally titled, "A Research Center for Augmenting Human Intellect." Few in the audience realized they were about to witness a defining event in computing history. Engelbart began calmly. He invited the audience to imagine having a computer display available throughout the day, instantly responsive to every action. Then, the giant screen showed his working environment. He typed text onto what appeared to be a blank electronic page. He created a file, added words, corrected mistakes, and changed formatting. These actions were revolutionary in an era when many programmers still communicated with computers through punched cards and printed output. The screen did not merely show a finished answer, it showed a living document that could be altered in real time. Engelbart used the mouse to move the tracking mark and choose locations. His hand traveled only a short distance across the desk, while the pointer crossed the display. He selected words and commands with a click. The device did not receive dramatic attention as a separate product. It appeared naturally as part of the work. This made the demonstration even more powerful. The audience could see immediately why a pointing device mattered. It connected physical intention with digital action. Engelbart then showed structured information. He created lists and reorganized their contents. He changed the display so that only certain levels of a document were visible. A complicated body of text could collapse into an outline and expand again. The computer was not treating a document as a fixed sequence of lines. It understood a deeper structure that the user could navigate. Engelbart moved through that structure with a speed and confidence that made the system appear almost magical. Next came links. He selected highlighted or addressed material and jumped to related information elsewhere. He followed connections within a file and between files. He opened text associated with graphical elements. Today, billions of people click links without thinking about the conceptual leap involved. A link turns a document from a closed page into an entrance. It allows information to form a network rather than a single linear sequence. Engelbart did not invent the later World Wide Web, and other pioneers independently explored hypertext. But NLS demonstrated a mature working environment in which linking was central to everyday knowledge work. Live Video connected Engelbart in San Francisco with colleagues in Menlo Park. In collaborative mode, he and Bill Paxton shared the same material while speaking through audio and video, and Jeff Rulifson later explained software from a remote console. The scene anticipated video conferencing, shared screens, collaborative documents, and remote technical work before the ARPANET had begun normal operation. Engelbart also showed how the group used NLS to create and revise reports. Team members could add annotations and messages. Search tools could locate contributions by a particular person or retrieve information related to specific terms. The system preserved relationships between ideas and participants. It was not merely a word processor. It was an evolving organizational memory. Engelbart wanted the computer to help a group understand not only the final document, but also the process through which knowledge had been created. The screen shifted among computer text, graphics, Engelbart's face, his hands, and live images from Menlo Park. Separate places and forms of information had become one shared environment in which distance mattered less and documents remained alive. When the 90 minutes ended, those who understood what they had seen were astonished. The phrase, "mother of all demos," was applied later, but it captured the extraordinary density of ideas revealed that day. The presentation included the public debut of the mouse, interactive text editing, hypertext, multiple views in Windows, shared documents, remote collaboration, video communication, sophisticated searching, and a philosophy of networked knowledge work. Many of these technologies would become familiar only after years or decades of further development. Engelbart had not shown a commercial personal computer. NLS ran on an expensive shared machine and required specialized equipment, but he had shown the pattern of the future. One person could sit at a workstation, manipulate information directly, communicate with others, and move through a connected world of knowledge. Success on the stage did not guarantee success afterward. Engelbart's vision remained difficult to explain, fund, and distribute. NLS was powerful, but its command structure and chord key set required training. New users could find it intimidating. Engelbart believed that serious knowledge workers should develop advanced skills, but the emerging computer industry increasingly favored systems that were easy to approach without extensive instruction. There was also a tension between Engelbart's broad mission and the narrower goals of organizations paying for research. He wanted to improve collective intelligence and help humanity address complex problems. Sponsors often wanted specific technical results. As government funding priorities changed and management pressure increased, the Augmentation Research Center began to weaken. Important supporters moved on. Members of Engelbart's team left for other institutions. Several joined the newly established Xerox Palo Alto Research Center, known as Xerox PARC. Among them was Bill English, the engineer who had built the first wooden mouse. At PARC, researchers developed new interactive systems, including the Xerox Alto, which used a bitmap display, windows, graphical elements, networking, and a mouse. English's group created a ball-based mouse that allowed smoother movement than the original perpendicular wheel design. The work at PARC did not simply duplicate NLS. Researchers pursued different goals and redesigned many ideas. They emphasized visual interfaces, icons, overlapping windows, and direct manipulation in forms that were easier for a broader range of users to understand. Some parts of Engelbart's vision, especially advanced hypertext and deeply structured collaboration, received less attention. Other parts, particularly the mouse and graphical workspace, moved closer to commercial reality. The chain of influence continued. Visitors from Apple saw graphical computing at Xerox PARC. Apple engineers then developed their own systems and commissioned a mouse that could be manufactured more cheaply and survive everyday consumer use. The Apple Lisa, introduced in 1983, included a mouse-driven graphical interface, though its high price limited its success. The Macintosh followed in 1984 and brought mouse-based interaction to a much wider public. Apple simplified the device to a single button, reflecting a philosophy of reducing visible complexity. Microsoft and other software companies expanded graphical interfaces across the enormous market for IBM-compatible personal computers. As word processors, drawing programs, desktop publishing tools, spreadsheets, games, and operating systems adopted pointer-based controls, the mouse became a standard part of the computer desk. By the end of the 20th century, millions of people used one every day without knowing Engelbart's name. The wooden block had evolved into plastic shells containing rubber-coated balls, optical sensors, scroll wheels, lasers, wireless transmitters, programmable buttons, and ergonomic curves. Yet the fundamental relationship remained remarkably stable. Move the hand, and the pointer moves. Indicate an object, press a button, and the computer responds. An action that once astonished a conference hall became so ordinary that people stopped noticing it. Engelbart himself did not become wealthy from the mouse. The patent belonged to SRI, and it expired before the device became a mass-market necessity. His original goal had never been to build a consumer empire, but the gap between his influence and public recognition was still striking. In 1977, SRI transferred the NLS project to Timeshare, where the system continued under the name Augment. Engelbart worked there for years, but the momentum of the original research center was gone. He retired from that environment in the mid-1980s and continued advocating for his ideas. With his daughter Christina, he later established the Bootstrap Institute to preserve and advance his mission. Recognition arrived slowly. Engelbart received major honors, including the Turing Award and the National Medal of Technology. Historians, engineers, and designers revisited the 1968 recording and recognized how much had been demonstrated in a single event. The mouse became a symbol of his achievement, but Engelbart sometimes worried that the symbol distracted attention from the larger purpose. He had not wanted simply to make computers easier to operate. He wanted to create systems that improved how organizations learned and adapted. His central concern was collective intelligence, the ability of groups to understand complex situations, combine knowledge, make decisions, and improve their own methods. Modern computing fulfills parts of this dream. People edit shared documents, attend video meetings, follow hyperlinks, search enormous collections, and collaborate across continents. Students reach distant libraries, medical teams consult remote specialists, engineers share designs, and families speak through screens. Each activity resembles part of the world Engelbart demonstrated. Yet the results are not always what he hoped. Networks can spread confusion as quickly as knowledge. Powerful tools can fragment attention rather than deepen understanding. Organizations may adopt faster communication without improving their ability to solve problems. Shared information does not automatically produce shared wisdom. Engelbart believed that technology, human skills, and organizational practices had to evolve together. Giving people a new tool was not enough. They also needed better methods for using it, evaluating it, and improving the system around it. This is why his revolution remains unfinished. The story of Douglas Engelbart is often reduced to a simple sentence. He invented the computer mouse. That statement is true but incomplete. Engelbart conceived the pointing device, and Bill English built the first prototype. Together, with a talented research team, they integrated it into NLS. The mouse mattered because it belonged to a complete vision of interactive computing. Without the screen, structured documents, links, commands, and rapid feedback of NLS, the wooden device would have been an interesting mechanism searching for a purpose. Within the system, it became a new form of human expression. It allowed intention to move visibly across digital space. The same is true of the mother of all demos. Its importance did not come from predicting a list of future products. Engelbart was not showing separate previews of a mouse, a video call application, a word processor, and a website. He was showing how these capabilities could form one environment for thought and collaboration. The audience saw a person create information, organize it, link it, share it, discuss it, and change it without leaving the computer workspace. The integrated experience was the real invention. More than half a century later, the original demonstration still feels strangely modern. The black and white video is grainy, the equipment is large. The text display is primitive by modern visual standards. Engelbart speaks in the measured language of a researcher rather than the dramatic style of a modern product launch. Yet his actions remain recognizable. He moves a pointer, he clicks a link, he edits a sentence, he changes a view, he calls a colleague, he shares a screen. The technological surface has aged, but the pattern of interaction has survived. The mouse evolved from wooden wheels to rolling balls, optical and laser sensors, wireless connections, scroll wheels, and specialized ergonomic designs. Trackpads, touchscreens, styluses, voice systems, eye tracking, and virtual reality controllers introduced alternatives, yet the mouse remains valuable for precise desktop work. Its endurance reflects the strength of Engelbart's insight. The brain quickly learns the relationship between motion on a desk and motion on a screen until the device seems to vanish, leaving only intention. Douglas Engelbart died in 2013 at the age of 88. By then, computers had become smaller and more powerful than almost anyone in the 1968 audience could have imagined. Billions of people carried networked computers in their pockets. Video calls crossed oceans. Hyperlinks formed the structure of the web. Shared digital workspaces connected offices and homes. The mouse had become one of the most recognizable objects in technology. Yet the deepest question Engelbart asked remained open. Can computers help humanity become better at solving its most urgent problems? Faster machines alone cannot answer that question. Larger databases cannot answer it. More messages, more screens, and more connections do not automatically create understanding. Engelbart's work suggests that the real challenge is designing a relationship among people, tools, knowledge, and institutions. Technology must help users see structure, preserve context, test ideas, learn from one another, and improve the processes by which improvement happens. Return one final time to San Francisco on December 9th, 1968. The hall is dark, and the enormous screen glows above the stage. Douglas Engelbart sits at his console with an earpiece in place. His colleagues wait miles away beside the remote computer. Engineers watch the video signals and communication links, knowing that a single failure could interrupt everything. Engelbart places his hand on the mouse and begins moving through a world that does not yet have a familiar name. He is not merely controlling a cursor. He is demonstrating that information can become a space in which human beings act together. A document can become dynamic. A reference can become a doorway. A screen can become a meeting place. A computer can become a partner in thought. Every time we click a link, reorganize a paragraph, join a video conference, share a screen, or edit a document with someone far away, we repeat a small part of that moment. The wooden mouse was simple, but the future it helped reveal was vast. The mother of all demos was more than a successful presentation and more than a collection of inventions. It was a message sent forward through time, asking humanity to imagine not only what computers could do, but what people could become with better tools. We have adopted many of Engelbart's technologies. We are still working toward his purpose, and perhaps that is the most important part of his legacy. The revolution he began is not a finished chapter in computer history. It is a challenge that remains in our hands every time we touch a machine.